Welcome to Geometric Models. In this lecture I'm going to talk about vector spaces. Assume in an example that a person A has a collection of items with certain numbers, 3 bags, 5 chairs, 3 screwdrivers and so on, and a person B some number of bags, chairs, screwdrivers and so on. What can you do with this? Well, you can collect all those numbers into a tuple, and these are elements of a vector space, namely real numbers to the power 6. Further questions you can ask are, for example, how much of each item do person A and B have? So person A and B have A plus B. This is also an element of R to the 6. You can also visualize their possessions. You have here the bags, here the chairs, here the screwdrivers and so on, and then just plot their numbers that they had. Something like this. This would be A, and person B would be something like this. It doesn't have to correspond with the actual tuples that you saw before in this example. So this would be then person B. And then if you want to see what they have together, well, you just add up at each place, taking the sum of this plus that. It would be something like this here, and this would be way up here, and this would be, say, right here. So, in other words, adding these tuples makes sense. But also subtraction makes sense. But there's also some neutral element in the vector which counts everything as 0. If you add it to some tuple, possession tuple, it doesn't change. You can also scale. Let's say they want to double their possessions or something like that. You multiply each of those entries with 2. So this comes and brings us to the concept of vector space and vector. So vector is any element of a vector space. So we have to define vector space also. We can take the elements of a vector space, vectors, and we can add them, and we can scale them. So addition is like this. You have a function plus taking 2 vectors to another vector, and it has to satisfy the laws of associative, A plus B plus C equals A plus B plus C. Something else that you need is commutative. A plus B equals B plus A. What you also need is a 0 element or a neutral element. The existence. So there exists zero in V such that A plus 0 equals A. And the existence of inverses. For any A in V exists minus A in V such that A plus the minus A equals the neutral element 0. The important is that these things exist in V. You might have some structure and you perhaps might know what could be acting as a 0 element or as an inverse. But if it's not part of V, then V is not a vector space. It has to be included. Also have is scalar multiplication. So you take a real number and a vector and obtain a vector. And it has to satisfy these laws. You have take 2 scalars times a vector V equals alpha V plus beta V. If you take a scalar and multiply it with a sum of 2 vectors, you get this. So, usual kinds of laws of arithmetic that you would expect. But what is also important, scaling matches. If you scale a vector with the number 1, you get the same vector. There's one huge prototype for vector space, something which generalizes the example that we had. Namely, so I call this prototype. If M is a set, any set, then you define this one here, the set of all functions from M into the reals. And these form a vector space. You can check all these laws that you have to, so that this has to satisfy. In the example, M is this set of bags, chairs, hats, and so on. So 6 elements, but in this example, M is the set of bags, chairs, and so on that we had. This R to the M would be corresponding to tuples with 6 entries of real numbers. If you have a vector space, and that's why this example that we had, this big one, is prototype, is important. If you have a vector space, you can have a subvector space. Subvector space, or a linear subspace. This is V, a vector space. And if you have U, a subset of V, which itself is a vector space, where the addition is the one from V, but you take only elements of U to add with each other, and the scalar multiplication is the one from V, also restricted here on the vectors of U. So if you have a subset of a vector space, you want to check, is it a vector space? Well, there's good news. Good news. You don't have to check the whole list of laws that need to be satisfied, because many of those laws are satisfied already here, and then they're satisfied here also. But one thing, the existence of things, these have to be satisfied. So, first of all, need only check first, is the 0 element of V already in U? If that is the case, you go on. If not, then you know it's not a vector space. Second, what about this one? If x, y in U, does this imply that x plus y in U also needs to be satisfied? And if it is satisfied, then you have a vector space together with 3. If alpha in R and x in U, then the question is alpha x also? So we need to check these 3 rules instead of the whole list of axioms that you have for a vector space. So, is this neutral element, is the 0 in U? If 2 elements are in U, then is the sum also in U? And if a vector x is in U, and if you scale it, is this scaled vector also in U? Examples of such a thing is given by the solution space of a homogeneous system of linear equations. We've written this as Ax equals 0. Here A is again an M times N matrix, and we are seeking the solution in R to the N. This is a very important example of a linear subspace, and later we will see that in R to the N, any linear subspace is the solution space of such a linear system. Thank you very much.